So you have an initial condition, which is randomized. And then via propagating that initial condition in that recurrent neural network, you're changing that pattern time by time. And eventually you're settling in one pattern only. It has no dynamics. Why doesn't it have dynamics? It's because for networks where the connections are reciprocal and the activity of the units can either be on or off, you can show that there is an energy function that is always decreasing. So this is the proof of the fact that you have an always decreasing energy function. Theta is a threshold. Let's imagine it's 0 to simplify our discussion. So it's 0. Now we define an energy function as the energy of every pair of neurons, ij, so the sum of the activity of every pair of neurons, ij, times their weight. There is no theta. The delta energy for iteration step you can compute by saying, okay, what happens if I iterate the network once? You're separating then the activity from the contribution of neuron 1, wij, j2sj, so basically one direction, plus the effort that is going in the other direction via the coming back weight. Now, wij and wji are the same. Hence, the sum of all of those energy patterns originally is equal to, the minus half disappears because it's going to be 2 times wij, because wij is equal to wji. So the reciprocal in the vocal connections, theta 1 is 0. And so this value, the total energy of the system, is always going to be decreasing at every single step. This is why you find a necessary fixed point attractor in the energy landscape of this network. Every pattern you have is a folding of this space. And when you start with a random initial condition, your ball is going to go down only in a single path. It doesn't get confused. It doesn't stop in the middle. It always settles. Questions? So if we draw a different bunny, will it recognize it as a bunny? Well, I mean, it's basically a pattern completion device. So it's not recognizing anything. It doesn't have output units that say bunny. What it has is the picture of a bunny, and that picture of a bunny is the stored pattern. The big word here on Hopfield networks that you will encounter once again in the project is called content addressable memory. In your computer, you have a random address memory where you can always decide an arbitrary place to save the pattern you want. In the Hopfield network, you create a pattern, you store that pattern via Hebbian learning, and you can retrieve that pattern via the iterations. But it has the caveat that it does not have infinite memory. It cannot store infinitely many patterns. And in fact, the number of patterns, uncorrelated patterns that it can store, there's a proof that shows that you can store about, I think it's 0.3 patterns per neuron. So it's about 3, for every 3 neurons you can store a pattern, if the patterns are uncorrelated. If the patterns are using parts of each other, then you have ambiguities in how to settle. You can imagine a Hopfield network with 2 sides where side 1 is a house, side 2 is a little kid. And then if you store 3 pictures, one of only the house, one of the little kid, and one with the house and the little kid, different initial noisy conditions will settle in one of these 3, but also potentially in only parts of these patterns. If you if you train now a network only on the house and on the kid, and you present a initial condition that includes the house and the kid, both are going to come back. I don't know if that metaphor comes clear without me making a drawing. Didn't want to spend so much time in here because you will still have the project to go through. So Sam, this answer make sense to you? So it will not recognize something as a bunny. It will settle on that particular memory that happens to look like a bunny. The Gazzaniga triangle idea is that you have the sorry, I interrupt you. You unmuted yourself, so please come in.
Oh no, I was just wanted to say that it makes sense now. Yeah, thank you.
Okay. How about the rest of you guys? So is this clear? So we, in a reciprocally connected recurrent neural network with symmetric weights, you have a single fixed point attractor, and therefore you can store multiple patterns.
Actually, it's not that clear how a single fixed point attractor translates into being able to store multiple patterns. Or maybe it's just my misunderstanding of something.
So unfortunately the connection is not good today, so I missed what you said. Can you write it on the chat? Drum roll. I'm gonna get my iPad so that I can sketch. Just a second. Oh, I left it downstairs. Oh, I don't know where the pen is. Oh, fuck it. I'm not gonna do iPad today. It's not very clear how a single fixed point attractor translates into the ability of storing multiple patterns. Yeah, the iPad would help now. But imagine that you have a small network, say something you can hold in your mind, say 5 neurons. Now, you want to store a pattern. Say that 2 of the vertices now are active. To store this pattern, you will then train the weights of the network to say that one neuron reciprocally excites the other. The 2 that are participating in the same edge are exciting each other. When you train that, okay, so you finish that training, and that those 2, that one edge is now strong. So if you start with a pattern that includes one of those 2 neurons, then it's likely that the second neuron is going to come alive. Is this clear? What happens with the other 3 neurons? Oh, well, the other 3 neurons, we want them to be off. So the 2 neurons that we now have active, they are going to have to say, inhibit those neurons. I'm going to add negative weight to that side of the pentagon, right? Now imagine I have another network and also a pentagon, and I train something else in that network. So basically the bottom part, so the other 3 neurons, okay? So now the other 3 neurons are going to be exciting each other reciprocally, whereas the 2 initial edge neurons there are going to be inhibited. Good. Now stick with these 2 networks. One has trained like one edge of 2. The other one has trained a connection between the bottom 3. Okay, so we have pentagons. If everybody is with me until now. Now make a network of 10 neurons just by joining the 2 without connecting them. You basically have now different kinds of combinations from your initial conditions. Now you didn't train this new network, but it has in effect 3 different attractors. It has the attractor containing the first 2 edge, it has the attractor containing the other 3 edge, and it has the attractor containing the 3 edge plus the 2 edge. If you start with initial conditions for these 10 neurons that are randomized, it will settle in one of these 3. So you have now a network of 10 neurons that has 3 fixed point attractors. Does this Gedankenexperiment help you in understanding why you can have multiple attractors? Now, if you're now training patterns that are not correlated, because I just gave you an example of patterns that are not correlated, then you can bind them together. You can continue to add them in the network. The network starts forgetting, starts having contradictory weights the moment that we train patterns that are correlated, that have pieces of each other. So, did this help? Yeah. The project hopefully will help you. And then you can also start playing with some variants of this network, because the Hopfield network is trivial to write. And that's also why it's so nice to look into the Jechter-Weiliger plot. Create a network with different sizes and consider, what kinds of storable patterns it can have. The memory capacity of the Hopfield networks is bad, but it has this nice analytical property of always settling into a single attractor. If you now connect this network way more arbitrarily by randomly connecting a bunch of neurons, say you have now 500 neurons, and you connect them all in weird ways, and you give an input that is also a random input, what's going to happen is what Radhika mentioned before. You're going to have some sort of, you're going to set a ball in motion. And that ball is going alter state to state to state to state. You're already seeing this in the Simple Neural Network project. This is why we've introduced transfer functions in the Simple Neural Network project. The idea there was that a random network converting weights will create some sort of ongoing propagating activity. What I'm going to do next, I'm going to tell you a set of interesting predictions from a randomly recurrent discrete neural network. It's been published a couple of years ago. And I think it's a 500 neuronal network. And so let me explain to you how this network is created. So you take that code in the project with 500 with neurons and make a random network 500 neurons. Take out the self recursions just to make the problem simple, but keep the network recurrently connected, neurons connecting to its own peers randomly. Press play by entering some sort of initial condition in that system, or by maybe plugging in an input to a subset of the neurons, that is creating a bias to a subset of those neurons. That activity is going to start to percolate. Now let's plot that activity. Okay, it's 500 neurons, so one way in which you could plot that activity is by having the state vector plotted side by side. I'm going to show this to you in MATLAB in a second. But plotting them by side, and then you can see, okay, so where does the network go? Another way to do it is by averaging the activity of all of the 500 neurons per time step. So you get per time step an average activity of the entire network. You've projected effectively the activity of the 500-dimensional problem to one additive dimension, to one output dimension. The left plot here is the time series for 600 time steps for this random network. And you see that it has some sort of oscillatory ability, and you keep looking only at the side of the autonomous dynamics for the moment, and that means that that's what the network does when it's given a stimulus. When it's let to process spontaneously, like you just jiggle a little bit and it starts and it does this. So the average activity of the network seems to oscillate, and it seems to oscillate in non-periodic ways. I mean, it's not exactly periodic. It goes up and goes down. So what's it doing? Well, it's doing that. Then you take a subset of the neurons and you give them an input, a specific input. something like you're opening your eyes, and now into this input of 500 neurons, say to 50 of them, you give a picture. Now, how do you distribute the picture through the pixels? Any way you like. Just give 50 values to these pixels. So choose 50 pixels randomly, give 50 values, but keep them. They are now a stimulus. So we're saying that this network is now getting an input for a subset of those neurons. What you observe here are two things: the autonomous dynamics and the stimulus force dynamics. The stimulus force are given an input to the network. The autonomous dynamics is without a network input. On the right side, you see what we call a first return map. A first return map is plotting the activity of the network at time t versus the activity of the network at time t plus 1. And here we're plotting the average of the activity of the network at time t and the average activity of the network at time t plus 1. The network, when it's in spontaneous mode, it is exploring. So here we have 10,000 points in this network. So on the left here you have only 600 time steps, but on the right you have 10,000 points in the time series. So a lot of states. So the network goes from one state to another, and then goes from another state to another. So you could, for example, have an average activity of, say, 0.53.5 over here, and then it produced an average activity of 0.52. These networks have sigmoidal units, so between 0 and 1 and bounded, and because they're going up and down, the average is naturally close to 0.5. But the point here being, even though this is a completely randomly recurrent neural network and it's running spontaneously, its activity in its heart is occupying a cloud of points that is a subset of the space. And that subset doesn't seem random at all. It seems like it has structure. That attractor, that multidimensional attractor of the 500 neural network that is acting spontaneously, have the activities falling within only one subvolume of the entire space. Big words, but the volume here is a 500 neuronal volume that is projected to one dimension in the average, and then we're looking into the relationship between the past state and the next state. So the past state and the next state fall into this cloud constrainedly. Then you add the stimulus on it, and what you see is that the stimulus force dynamics have reduced the dimensionality of that cloud further. So not only you already had a little bit of structure in the original cloud, when you forced the dynamics upon it by adding a stimulus, whatever that stimulus might be, just made it constant, you have reduced the dimensionality of the output, and you've created a one-dimensional manifold where those states can be. That's very weird. We haven't trained this network to do anything, and we produce a random network, and it actually has places of the phase space it likes to go. And when you give a stimulus, it constrains the places where the network can be. Ask me about any words that I've used up until now, if you need. Manifold, volume of phase space, first return map, autonomous dynamics, stimulus force dynamics. But first things first, do you understand how this network is formed? It's a 500 randomly connected neural network. Do you understand the input? The input is one static, one-dimensional vector. And then you let it run. This is a representation of a vast class of networks. And this is one possible network of millions of networks with 500 neurons. And this paper is there because they show that stimulus presentation in randomly recurrent neural networks reduces the dimensionality of the output. The exciting bit is that the same thing happens in biology. Do you have questions about about these two graphs?
My question was about I'm wondering why this happens. Why is there dimensionality reduction? Because I don't think I understand how that
It's
arises.
a very good question. Is the fundamental question in this project. Anyone has any ideas? I'm going to use words from dynamical systems, but if anyone would like to contribute their intuition about why do you see a reduction of dimensionality of the stimulus, you're welcome to do so. You're pushing. Ultimately, it is because you're pushing the network in certain directions. And you're pushing it systematically, continuously. That's the intuition. It doesn't happen for every random network. It happens on average for a large class of random neural networks. They have to have, so there are some other mathematical criterion that will sharpen their ability to reduce the dimensionality, and one of them is that these networks must have large spectral radius, which means that their first eigenvalue is high. But the point here is that the network is coercing. Like once you add the input, the network is coerced into certain parts of the phase space. You're skewing the activity of that network, and you're not letting the network operate on small sensitive stimulus, but you are injecting energy in the network, and that is that energy of that constrains your trajectory. More than this, we would have to work on eigenvalues and eigenvectors of these matrices, and I was not going to do that. I just want to present this face value, and then I'm going to add that training networks will do it even more so. So if you use a Hebbian learning function, you will constrain the dimensionality of the network even further, Hopfield style, even though these are networks that no longer have that kind of symmetrical relationship, so in a control condition. Now you take that network and you make a change. Add the simple network project with the Hebbian learning project. Bind them together. Make a project for your end project here. Take a simple network, put Hebbian learning in it. What happens? You constrain the structure of the network further by imposing the statistical regularity of your input and constraining the network space to be along the directions of correlation of what you're putting in. Here's some biological data for you. This paper in 2010 said stimulus onset quenches neural variability. And this is a widespread cortical phenomenon. This is a paper by Patricia Churchland and others. I think it's the, not Patricia, is this the daughter of Paul Churchland and Patricia Churchland. So Mark, is it a lady, girl? I don't remember. Anyways, the point here is that when you add a stimulus to a neuronal network in a primate that is doing a task, and you measure the activity on a certain part of his brain, you observe a reduction in the variability of the neural area measured according to the Fano factor. The Fano factor is, it computes the ratio between the standard deviation and the mean of a variable. So it basically is a simple measure of the amplitude of the variability. And here in each of this, let's focus for the moment on the figure on the right side of the slide. Here for every two plots, you have one experiment going on. So here on the top left, you have an experiment in which you have an oriented grating. Okay? And you're measuring neurons in the occipital cortex, V1. And when you turn on the presentation of that stimulus, you see a reduction on of the Fano factor. There is, at first, there's a bit of confusion. as the network might be going in a transient moment, as we call it. Notice the average activity of the network is rising, but the amount of variability is lowering. In V4, if you have a colorful stimulus on the right side here, on the right top, you observe the same phenomenon. So in many of these phenomena, although you see an increase of the activity, you see a reduction of the variability of the data. These are two moving gratings that do like this, and so you have that illusion of motion, and so you're measuring MT, which is the medial temporal cortex. Or also moving the medial temporal cortex, you present a random dot pattern moving. Also see a reduction of the phenofactor. Or in the lateral interparietal cortex, here LIP, you have a choice paradigm in which the monkey has to look to the green dot and gets juice if he gets to the green dot. Also there, when you present the stimulus with a reward, you have a reduction of the variability. When the monkey does a reaching motion, when the monkey sees correlated dot patterns going in other directions. So it is a pervasive phenomenon. The point of this paper is that this reduction of variability is a very pervasive phenomenon. And this paper came in 2010. The paper that I presented to you earlier is 1995 or something. So 15 years later, people figured out that's how it was, even though there are two big unexpected findings here. One, randomly connected neural networks do not have random output. They have very specific output that go within a certain cloud of points. Second, adding stimulus, instead of augmenting some sort of energy, which it does by activity, in a measure of activity, spikes per second, reduces the variability of the neural activity. I take this paper because it represents this class of phenomena very deeply, but this is the reason why brain-computer interfaces work. You produce a stimulus and the output is constrained to a lower dimensional space. And this lower dimensional space, then we can retrieve via, for example, linear regression, multilinear regression, to obtain a particular pattern. I don't want to go much further for today, also not to tire you. I think that we've had a long day, you already have a lot of thinking to do, but I do, and I'll probably, I think that this is a fair place to stop, but I wanted to show you a bit of MATLAB code that implements a recurrent neural network where you can observe this phenomenon. So I have here my MATLAB already fired up, and I wrote a piece of function that is called reservoir. And it creates a dynamical reservoir. There will be a reason why I'm using this word, of 15 neurons. And I'm using a random seed that I previously selected because it looks good. But you could do this experiment many times, select other random seeds. Just don't want to belabor here the point. To produce effectively the same outcome from the paper of Cesac and Dossé. So here we have a representation of that same network. On the top left, you see the activity of the neurons. These are sigmoidal neurons going from 0 to 1 over time. And because you have 10,000 data points, you see them as kind of colors. But if you looked at the individual neurons, you would see that many of them are actually oscillating. I don't know if you can see this, but ask questions if you don't understand. So the top graph here then has the activity of this network, both at the spontaneous level And you see that it settles in some sort of periodic attractor, but it's not perfectly periodic because it looks fairly noisy here in the time series. Now I'm looking into the top representation of this. The top right representation is the average activity of this network per time step. So I'm just averaging the columns of the top left. I average all of them on the top right to have a representation of the entire activity of the network. And this is how it looks like. It looks like a juggly time series. There's a little bit of an oscillation going on. It's an aperiodic oscillation. This is a highly chaotic attractor for those of you that care about dynamical systems. The fun thing here then, so after some time, I present a stimulus, and then it changes the activity of that network. So the stimulus has been presented at 3,000 milliseconds, and something weird happens for a little while. That's a transient. The same something weird that happened for a little while as we presented the stimulus in the paper from Churchland. So here you notice that there is, for a little while, an increase of the variability when you present the stimulus. And not in all cases, in fact. But this is the so-called transient of that stimulus. So before it's settled on another different attractor that is a little bit more lower dimensional than the original one, notice the attractor that comes afterwards, you have a bit of a variable, like, whoa, what's the network doing? I got this new input. I will have to resettle. I'll have to, calculate a bit where I want to go, and then I go into this lower dimensional attractor, much simpler periodic attractor. The first return map is the on the bottom right is the average activity of the entire network of time t against time t plus 1. Average activity at time t against average activity at time t plus 1. And on the bottom left, you have the connectivity matrix, which is random. And in here, I have a second return map. That's why it looks 3D. So the second return map is t against t plus 1 against t plus 2. So every point here includes 3 moments in time. Now, next, one after next. So that's why it looks neatly three-dimensional like this, because you're varying this activity in 3 dimensions. But I honestly only present this because because it's so pretty to see these point clouds rotating when you don't know what they mean. Some points here are red. You cannot see them, but they are the attractor to which the activity settles, and the lower dimensional attractor that we were talking about. Done. I'm going to put this code online if you want to test and play. So a couple of ideas that you can also work with as you're considering about your project, or you can also look into this paper for the journal club. That's all I had for today as far as content goes. Next time we're going to talk about how evolution comes up with ideas for randomly recurrent neural networks that actually can do fun stuff. And I'm also going to talk about how to train these randomly recurrent neural networks in the case of echo state networks. And you will be going through the Hopfield Network project, which I'll make available as soon as we finish this lecture today. It's been a while since you've asked a question. It always scares me a bit. But I understand that this is a bit of a chunk to bite on. Talking about recurrent neural networks, first lesson, woof, all of this. There's not much. It's just randomly recurrent, and then this fun stuff happens. Or you create them symmetrically connected, this fun stuff happens. There's not much more material. Now it's a matter of really wrapping your head around these concepts and playing with them sufficiently until the intuitions start dawning on you, until you start training your own networks to settle on attractors and feel that you will understand. Some people said that making a new attractor is actually an epiphany in your brain. So when you have an epiphany, that sense of aha, that is a new attractor that has just been wired, and you got a little bit of dopamine to go along with it. I don't think that there's any proof for that, but it's a very lovely thought for a neurodynamics guy. Okay.